Component form of a vector. The component form of a vector AB with initial point A, x1, y1, and terminal point B, x2, y2 is given by, we subtract the x's and we subtract the y's. And the component form of a vector is denoted by these symbols which are chevrons. So we have an initial point A and a terminal point B, and we want to write this in component form. So we could have, find the component form of AB with initial point A, 1, negative 3, and terminal point B, 1, 3. Let's see what that looks like. 1, negative 3 down here, so there's the initial point. And B is 1, 3. 1, 1, 2, 3. So we are up here. So here is the vector right there. Now, we want to represent the vector in component form, which means we're going to put the initial point on the origin, and we want to draw the exact same vector from the origin. That represents component form. So the component form is 1 minus 1, which is 0, and then 3 minus negative 3, which is 6. So there's the component form. So this vector with the original points is the same vector as the one now with just one point in component form. Magnitude of a vector in the coordinate plane. If V is a vector with initial point x1, y1 and terminal point x2, y2, then the magnitude of V is given by what we really have is the Pythagorean theorem here. If V has a component form of AB, then we've already taken care of the subtraction, just like we did in the last slide, and we can just do a squared plus b squared. So as long as you have 2 points that are not lined up either horizontally or vertically, you can draw a triangle from one point to another, and if you want the magnitude or the length of the vector, all we have to do is utilize the Pythagorean theorem. Find the magnitude of AB with initial point 1, negative 3 and terminal point 1, 3. Well, we already determined that the component form was 0, 6, so the magnitude of vector AB, which is denoted with what looks like absolute value signs, but in vectors this means magnitude. It's equal to the square root of 0 squared plus 6 squared, which is the square root of 36, which is 6. So the vector we had in the last slide has a magnitude of 6. Vector operations. If A is a component form of vector A and B is a component form of vector B, are vectors and K is a scalar, then the following are true. You can add vectors, you can subtract vectors, and you can multiply vectors by a constant. Find 2w plus y for w is this vector, and y is this vector, and z is that vector. So we want 2w plus y. So we want 2 times w, which is 2, negative 5. And then we're going to add on 2, 0. And we do exactly what you might think. This is going to be 4, negative 10 when we multiply by 2. And then when we add, we just add the x's, which is 6, and add the y's. That'll be negative 10. Find a unit vector u with the same direction as v, 4, negative 2. To find the unit vector, or in other words, a vector with a length of 1 unit in the same direction as 4, negative 2, you take the vector and divide by the magnitude of the vector. So let's find the magnitude of v. Magnitude of v is the square root of 16 plus 4, square root of 20, so 2 square root of 5. And so the unit vector is 4 over 2 square root of 5 and negative 2 over 2 square root of 5. So we can do a little reducing. We have 2 over square root of 5, and the y will be negative 1 over square root of 5. So this vector has a length of 1, or a magnitude of 1, and is in the same direction as 4, negative 2. Let DE be the vector with initial point negative 3, negative 3, and terminal point 2, 6. Write DE as a linear combination of the vectors I and j. The first thing we do is put this in component form. The x is going to be 2 minus negative 3, and the y is going to be 6 minus negative 3. That's going to be 5, 9. So to write it as a linear combination of I and j, is 5i plus 9j. Find the component form of the vector v with magnitude 7 and direction angle 60 degrees. So the component form is going to be 7 cosine of 60 and 7 sine of 60 degrees, that is. We have 7 times the cosine is a half, and 7 times square root of 3 over 2. Find the direction angle of P, which is 2, 9, to the nearest tenth of a degree. Find the direction angle. All right, so we have 2, 9, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right there, there's the vector very roughly. And to find this angle right there, we can use inverse tangent. So we have the inverse tangent of 9 halves, or y over x, or sine over cosine. Let's go to the calculator. In mode, we'll look at, I want the answer in degrees. So we do the inverse tangent of 9 halves, which is 77.471 degrees. Find the direction angle of r equals negative 7i plus 2j to the nearest tenth of a degree. Let's plot this point. Let's get an idea of where this point is. 1, 2, 3, 4, 5, 6, 7, negative 7, 2. So this vector is sitting over here, and we want that angle right there. Let's take the inverse tangent of 2 divided by negative 7. And we get negative 15 degrees. So that's actually in the opposite direction. So we got an answer of negative 15 degrees. So in order to find the angle we want, we have to add on 180 degrees. So let's add 180. And the answer is 164.1 degrees.